Good afternoon, everyone. This is Cameron Smith with TechLogix, and today we are going to be looking at some slides on the fiber optic workshop. This is a course we teach hands-on at CEDIA and across the country and really across the world in different places, teaching folks about fiber optic infrastructures, how to terminate cable, how to select different cables, and really why we're using fiber in audiovisual installations. Before we get going, a couple things I'd like to mention. In the little GoToWebinar widget, you will see a handout tab. You can go ahead and click on that. There's a PDF in there of a fiber optic pocket guide, which is pretty handy. It has a lot of the information that we will be covering today in a concise, summarized format. Also, as we work through this information, we will have a couple of questions undoubtedly come up. I encourage people to go ahead and type that into the question area in that GoToMeeting widget, and that way we'll get to the questions at the end. We have a fair amount of content to cover today. We're going to try to do this in about 45 minutes. That's usually about what it takes to go through this concise, kind of cut down, condensed deck. And with that, let's launch into it. So fiber optics, we are seeing more and more fiber penetrating that audiovisual environment, that audiovisual installation and infrastructure. And a lot of people talk about HDMI over fiber, or obviously networking over fiber. And in my opinion, there's a lot more to it, especially when we look at today's modern technology. There's a lot of moving parts to the fiber optic infrastructure. And I like to think of this in terms of media over fiber optics. It's more than just HDMI. It's more than just networking. Everything that fiber or everything that copper has done historically, fiber can do with one exception, and that's transmit power. And there's some major advantages to not transmitting power that we'll look at here in a minute as we kind of work through these slides. But what that means is fiber can handle our video. Fiber can handle our audio, it can handle our control, it can handle our networking. And because we have a much larger pipe to work with, a lot more bandwidth, a lot more data rate capability, that means we can do a lot of things simultaneously. We can do them faster, we can do them further. That's the nice thing about fiber. And for all of you who are new to the fiber optic infrastructure, the good news is it's not that unfamiliar. And what I mean by that, the different parts of the fiber infrastructure are very similar to the copper infrastructure. So if we look at it, we see things like bulk cabling, right? We're all used to pulling cable. We terminate it in the field. There is obviously bulk cable that we're working with fiber optics. Patch cords. Some people call these pre-mades. Basically, they're pre-terminated cords that come from the factory already with the connectors on them. These all exist in a fiber optic infrastructure. Specialty cables, things like direct burial, things like tactical cables, outdoor rated, UV rated cables. All of these things are available. And of course, if we're talking about cable, we should also be talking about connectors and installation. How do we actually work with these different cables in the field? Now, what's near and dear to my heart are the electronics. And this is an interesting area. This is what really, in my opinion, makes fiber optics work. Because fiber's been around for a long time, right? And there's a lot of installers, integrators out there who pulled fiber a decade ago. They put it in the homes, they put it in corporate businesses, but they never used it. So now when I'm doing these classes and kind of traveling around and talking to people, they say, why is today different? Why are we actually going to use fiber today when I thought we were going to use it 10 years ago and it never really came to fruition? And the reason is because 10 years ago, there really wasn't a lot to connect to it. It was a great pipe. It went in the wall. You know, we had it there, but it sat dark. There were no electronics to really connect our devices or connect our different sources and destinations together. That's changed today. There are extenders that leverage fiber for 4K 60, 444 HDR, and of course 8K. We'll talk about that here in a minute. Networking is increasingly going to fiber. So this rise of development behind the electronics portion of the fiber infrastructure has really pulled it all together and made this all work. So it's really important that we keep that in mind. But before we get into a lot of the technology and the physical properties, the physical pieces of this infrastructure, let's look at why. Why are we doing this? Why are we seeing the rise of fiber now? And this is a slide that should look pretty familiar to anybody who's doing AV and certainly residential installations. So we all have seen this resolution spread go from 4:3 aspect ratios, kind of our 480i and our 480p, that standard def box TV, up to 1080p, and now we're dealing with 4K. Well, this has worked out pretty well, and for most people who are dealing with 4K and these high definition signals and moving the high definition signals from point A to point B, we know that twisted pair, copper, has been the way to do it. And we also know that copper, through things like HD-based T extenders and different types of twisted pair extenders out there, it has historically had the bandwidth, the data rate capability to move those signals effectively. Now, we'd max out at about 330 feet or 100 meters. That's kind of the spec that we operate within in the twisted pair world, but that handles the majority of the installations. Now, one of the issues that we're seeing is 4K video, and anybody who's doing these residential installations where the latest and greatest displays are being deployed, we know that 4K 6444 HDR can exceed that 10 gig spec. Now, what happens if we're exceeding that 10 gig spec? And actually, HDR, these 4K 6444 signals, can go all the way up to 18 gig. Now, Cat5, by virtue of what it is, twisted pair, and I make the mistake of saying Cat5 because in reality it's Cat6, Cat6A, shielded cables. These all max out at about 10 gig. So how do we take an 18 gig signal and get it onto a 10 gig cable? Because we're doing this, and it works pretty effectively. Well, we do it by compressing the color space. Okay, and this is a chart that I really like. This tells the story that HDMI and certainly 4K is not all the same. So when we look at the different parts of the signal, when we take the frame rate, the color bit depth, whether or not we have HDR, certainly the different color algorithms, right? Depending on what we're doing with each individual part of the signal, the bandwidth, or what is appropriately known as the data rate, is affected. Now, a copper-based system, as I mentioned, twisted pair, so Cat5, Cat5e, Cat6, that maxes out at about 10 gig. In order for us to take these 18 gig signals, these bigger signals, and effectively transmit them over copper, we have to take that color space, the 444 portion, and compress it down to 420. And that's with these extender technology out on the market. It's known as a VLC technology. We work with it here at TechLogix as well. We take that 444, we compress it to 420, we transmit it over copper, and then we blow it back up. And that works pretty well. Now, it's not without artifacts. There is when you start to get into some really large image screens. I mean, you can see some color banding, but for the most part, it's a really beautiful way of taking a big signal and transporting it over a cable that's fairly limited. It works for today's technology. But as of January, we have an issue. HDMI 2.1. The HDMI 2.1 specs released. HDMI 2.1 supports 8K. Now, 8K is not like 4K 6444, 18 gig. 8K goes all the way up to 48 gig. So now we're looking at this 48 gig signal and all of the cool things that it can do with the ERC and the dynamic HDR. And we got to find a way to compress this all the way down below 10 gig in order to put it on a copper cable. And frankly, that's a really large ask. It's far too much compression in order to effectively move these signals, these 8K signals, over a copper cable without having major latency issues, without having major compromises to the actual individual parts of that 8K signal. This is where fiber really starts to become part of our installation, because fiber handles the bandwidth to take on this 48 gig signal. And there's something that I should mention. Very often when I'm teaching classes like this, people will ask me, well, that's great. I see 8K. I hear the 48 gig message, but is there any content? Are we talking about any content here? Is this real, right? And the thing that I like to remind people is 8K is not like 3D. 8K isn't even like 4K HDR, okay? There is 8K content out there. Anybody who watches sports and sees the instant replay where there's the zoom on the goal line or the zoom in on the batter's box, that's not because we have telephoto lenses. That's because we have the resolution. The 8K content is being filmed natively, and we can zoom in because of that. There is 8K content out there. TV shows are filmed in 8K. Movies are filmed in 8K. The problem has been there has been no consumer electronics to actually handle these 8K signals. That's changed, okay? With HDMI 2.1 as of January, and certainly anybody who went to CEDIA this year, you saw a bunch of 8K displays from various manufacturers, okay? This will be the first holiday season, you know, the November, the December 2018 holiday season, where we will see the consumer 8K technology hit. And for that reason, we need to be thinking about how do we wire for this. And that's where fiber comes into play. Now, it's not just about broadcast, because frankly, 8K isn't going to be deployed via broadcast in the way that we're historically used to it. We're going to see 8K coming from streaming media players. We're going to be pulling that content off of the internet. We're going to be putting it into these different media players. And then from there, we're going to be deploying it into our displays and our projectors. Now, that undoubtedly has an effect on our networks and our internet speed. Now, fiber to the home is a great thing. And this helps us as we're talking to a lot of our end customers out there. They get the value of fiber because of all the ISP, the internet service provider marketing around why you want fiber and getting fiber to the home. Now, that helps us as we look at creating an infrastructure that handles the amount of data for 8K and streaming. But that's not the only story that we need to talk about with networking and with fiber. I mean, if we look at the average middle class home here in the United States, we see that that home has about 23 different connected devices. And depending on who's in the different classes that we work with, you know, half the time we have people who say, that's it, only 23 connected devices. You know, they're the ones with their laptop bags. They usually have 4 or 5 different tablets and phones and computers. They're really well connected, right? And then the other half of the people say, wow, 23 connected devices, that's a lot. Well, this number is expected to go up to over 50 connected devices per average middle class home by 2020. And if we think about it, those homes really are seeing a proliferation of connected technology. It used to be just your laptop, your phone, your tablet, but now it's appliances, security systems, toys, all kinds of different devices are becoming web-enabled. They're connected devices, the Internet of Things. That puts a strain on these networks. And then on top of that, we have higher bandwidth media streaming. Broadcast is starting to turn into downloadable content. Things like DirecTV Now and Sling, Hulu, people are streaming their content directly from the web, and that all has an effect on our network. So as we're thinking about fiber, we're thinking about AV, but we're also thinking about networking. Very important in these connected homes of the future. That's not the only benefit that fiber brings. Okay, and before we get into the physical parts of the fiber infrastructure, which I promise we will go over today, we should also look at the other major reasons why fiber is of a lot of value here. And I mentioned as we kind of started that the one thing that fiber can't do that copper can do is transmit electricity. So it can't power itself. It can't power different devices. Now, the downfall of that is obviously we got to plug our different electronics in on either end. And that could be plugging it into an AC outlet, right? Our power outlets. It could be through power off of a USB port on a display. We see that on a lot of these products. It could be through, USB or HDMI connections, secondary whips. There's a lot of different ways you can power a device, but fiber does not transmit power. So we can't move the power and power our devices remotely. Now, what that does mean is fiber optic cabling is completely immune to power surges, static electricity, lightning strikes. We don't see any effect from electromagnetic interference, so EM interference, RF interference. Fiber is immune to all of this. That means that fiber can go into these installations where we have different ground potential issues, where we have heavy lightning, in the southern part of the United States, the Southeast, places like South Africa, right, where there's lightning activity, fiber's immune to that. Places out west where it's really dry and there's a concern over static electricity, fiber's immune to that. Major advantages of using a fiber optic infrastructure is the devices have immunity on each end from electrical issues. And then the other major advantage here is there is no bleed over. If we think about that installation, right? What did we all learn in school when we started studying AV and starting to take our tech classes? We don't trunk cables. So one of the big issues of a twisted pair installation is that when we take our different cables, right, all of our different extenders and networking, and maybe throw a control cable in there or an amp cable in there, and right, we Velcro it together or we zip tie it together. Well, we're never supposed to do that, because what'll happen is you'll have crosstalk amongst those different cables, and crosstalk can knock out the individual signals. That's why you'll have an installation where, hey, everything's working great. And then 10 days later, you get a call from the homeowner and they say, hey, look, I don't have any picture on this display. That's often from crosstalk knocking out the individual signals because our cables are being interfered with. Okay? Fiber is immune to that. That's why we see it in government. That's why we see it in medical applications. That's why we can use it in these very sensitive big installations in our CI world and in our professional AV world. Fiber is an ideal mechanism from that. Now, some other advantages: fiber is not corrosive. We're not dealing with a metallic mechanism here. We're dealing with glass or polymers, so we don't have to worry about the degradation over time. And then really, quite importantly here, modern fibers are very easy to handle. In fact, you can terminate these modern fibers faster than you can work with shielded Cat 5, shielded Cat 6. It's a little difficult on the webinar to get into this portion, but it's a nice part of the hands-on training that we do. And then fiber is very affordable. We've seen the cost come down. Obviously, as more people embrace fiber and fiber infrastructures, the economy of scale goes up and the cost goes down, and that's really what we're starting to see now. But enough about fiber. Let's actually start to look at the different parts of the fiber optic infrastructure. That's why a lot of people like to sign up for these different classes here. So there's really 4 different types of fiber that we're going to run into in our installations. And one of the things that I'll mention, I still make the mistake of talking about conductors, right? How many conductors do we have in the fiber? And that is not what we're talking about, because fiber is not conducting anything, okay? We're talking about strand count. How many strands of fiber do we have in those individual cables? Now, simplex fiber, the first one here on the screen, has one strand. Simplex is one strand, whereas duplex is two strands. And one of the things that, I always point out, so much of the fiber conversation is about future proofing. Okay, we turn to fiber because of all of this bandwidth that it has available to us to handle all these devices of the future. Well, if we pull simplex fiber, even if our devices ask for simplex fiber, one strand, we're really not future proofing. Now, I'd be remiss to not talk about simplex because it is available on the market, but I tell people never pull simplex. And the reason is, in the networking world, not necessarily AV, right? Because we at TechLogix, other manufacturers, make simplex-based devices where only one strand is needed to send an HDMI signal or a control signal or whatever you need to send. But in the networking world, you almost always need duplex. One strand is used for transmitting, one strand is used for receiving. It is the standard. Sticking with the standard means it will be the most cost-effective and most widely deployed. It is very important for us as we talk about our installations to, at a minimum, pull duplex fiber. Two strands. You always want to have those two strands. Even if you don't use both of them, two strands will allow you to future-proof. Now, two different types of fiber, and we'll look at these in a little bit more detail here in a minute. There's breakout fiber and micro distribution fiber. Both types have multiple strands within a single outer jacket. Now, breakout fiber, and you can get this in, different strand counts, a 2-strand, a 4-strand, a 6-strand, et cetera, breakout fiber has more heavily jacketed individual strands. So you have more strength as you pull back that outer jacket and you expose the individual strands inside. Okay, these are made to be broken out and go into your individual connectors, whereas micro distribution has less jacketing around those individual strands, but therefore you can have much, much higher strand counts. So you can have a very thin cable. It's a great part of the training, the hands-on training, where we actually see these micro distribution cables that are smaller than a Cat5 cable, right? They're really small cables, and you'll have 24 strands of fiber in that. Now, the micro distribution doesn't have as much protection on those individual strands, meaning that you have to go into a breakout panel, which we'll look at here in a minute, to actually give it strength and break out the individual cables and individual connectors. But two different ways to handle multiple strands of fiber is breakout and micro distribution. Before we get into that, let's look at the fiber itself, okay? So there's different parts to the actual physical fiber optic cable. And these are important because as we start to do the hands-on and we start to understand how these cables work, we have to understand the different components that go into making a fiber optic cable. Everybody's familiar with a cable jacket, right? That's what we see on the outside of the fiber optic cable. And that jacket can be plenum rated, it can be UV rated, you'll have water outdoor ratings on these cable jackets. A lot of different ways you construct it depending on the plastic grade and the different polymers that are used in the physical construction. It's when you strip back that cable jacket that you start to see some unique properties here. And the most visible part of the fiber cable is the strengthening fibers, also known as aramid yarn. Okay, this is what gives these cables all of its strength. Now, in the case of the fibers used by TechLogix and frankly a lot of the companies in the AV space, those strengthening fibers, that yarn is actually made out of Kevlar. Okay, and that Kevlar often has waterproofing gel that is built into it. It's coated on that yarn. So these fiber cables not only have incredible strength, and when I say incredible strength, I mean a 220-pound pull rating because of this Kevlar inside, but you also have waterproofing and the ability to have a wet rating because of the gel that's infused into this strengthening fiber. Now, once we pull back that fiber, we get into some unique properties here. We get into the coating, which is the outer plastic on the outside of that fiber cable, the cladding, which is a layer that's around the core. And the core is the actual glass, right? And in some cases, it's a polymer. In today's modern fiber optics, you will see cables that are made out of polymers, but it's still predominant to see these cores made out of glass. And it's the glass core that transmits your signals from point A to point B. We're dealing with lasers. We're dealing with LEDs, depending on the different technologies out there. That essentially allows us to transmit signals at the speed of light. Now, in the AV world, most people are very familiar with the term SSF. It stands for stronger, safer, faster. Now, this is a patented type of fiber that really is designed for that AV installation. Now, there's nothing different about it from a manufacturer, a spec standpoint from the fibers we think of in networking. What an SSF grade fiber does is it takes that outer coating, that outer jacket, not the big completely outer jacket, but the inner cladding, and it coats it with polymer. Now, the important part of taking this polymer and wrapping it around the core, wrapping it around the cladding, is that is going to give us strength, okay? If we think about these modern SSF fibers, and I think of it in terms of a window, okay? And this is what makes it very important, in my opinion, for the AV installation. Traditional fibers, the stuff that we worked with 10 years ago, was much like a traditional window on a house, right? If we throw a rock at a window on a house, it shatters. And for that reason, we had to be very careful with fiber. And this is where a lot of the misconceptions come in. People think that fiber is incredibly fragile, and historically it was, right? If we bent it too much, it could crack and fall apart, and then it was no good. If we pulled it too hard, it could crack and fall apart, and then it's no good. These modern SSF fibers, with a polymer coating this core, allow us to do some incredible things. And it's actually what's known as a bend-in-sensitive rating, meaning we can take these fibers and literally tie them in knots, okay? Micro bend ratings. You tie them in knots, and they still operate. Think of it in terms of that window on your house compared to an automobile window. You throw a rock at an automobile window, it chips. But the coating on the window keeps the windshield from falling apart, from that crack spreading, okay? That's what this polymer does in these modern fibers. It allows us to handle it roughly. It allows us to handle it with bare skin. It allows us to not worry about getting oils and debris, dust, things like that all over the fiber and having it not work. In my opinion, it's what makes the AV installation as robust as it is. Now let's turn our attention back to the different types of fiber, because this is important. We need to all make sure we understand simplex fiber is that single strand, that one strand of fiber under a single jacket, okay? But very rarely are we ever going to pull simplex fiber. It exists, but for the most part, in order to truly future-proof, we want to think about duplex fiber at a minimum. Duplex fiber gives us two strands to work with. One strand is used for transmitting, one strand is used for receiving. This is the standard in networking equipment. This will future-proof us for a lot of the AV equipment that we run into. Even if our AV equipment uses simplex, and again, we at TechLogix, we do make simplex-based electronics. Pulling fiber, future-proofing, we should think about duplex at a minimum. Breakout fiber, bulkier individual strands, and a multi-strand cable, so we can get higher strand counts under that single jacket. But this allows us to work with multiple different drops of cable, running them from point A to point B. These are also known as fan-out cables. And we can compare that to micro-distribution fiber. Micro-distribution fiber has multiple strands, strand counts from 4 strands, 6 strands, 8 strands, 12 strands, 24 strands. You get very high strand counts and very small pliable cables, but they don't have as strong of a outer coating on those individual strands. What we need to do then with those micro distribution cables is go into a breakout panel. The breakout panel is where we have all of our individual connectors. We take all of our different fiber legs, and we can then patch that to our individual points. Typically what we'll see with these micro distribution cables, that's what we're trunking between different buildings. That's what we're trunking between different racks. This is where we're moving a lot of bandwidth from point A to point B, but then once we get it to that point of demarcation, we branch it out from there. And typically the micro distribution will then go into a panel, a breakout panel, like what we see here on the screen, and then we will have our duplex fiber run out from here. That's where our duplex comes in. 95% of the applications out there use duplex fiber. That tends to be the standard. That is the 2-strand duplex riser rated cable. Now, obviously you see plenum, you see outdoor rated, you see tactical, you see all kinds of different other variations in there, but the vast majority of the time it is riser rated, in-wall rated, duplex fiber being pulled from point A to point B. Now, the next thing that we really need to get a grasp on is the different types of fiber. And there's 2 different types of fiber that we will be working with. So the first is single mode. And this is pretty important because this is a little bit counterintuitive. You know, people tend to think of bigger pipe means I can go longer distances. It's kind of the way people think in terms of, you know, bigger means faster and stronger. Well, in fiber, it doesn't really work that way. Single mode can be compared and contrasted to multi-mode. And the way to really keep these separate is single mode is used in applications that are longer than 1,000 feet, whereas multi-mode are going in those applications that are less than 1,000 feet. Now, that's not to say that single mode can't be used in less than 1,000 feet. Really, frankly, single mode can handle any application from 1 foot all the way up to 20 kilometers. No problem. It's where multi-mode really you're starting to max out at 1,000 feet. And if we look at why, this is where I say it's a little counterintuitive. Multi-mode actually has a bigger glass core. It has a bigger pipe. And that bigger pipe means that we can send more stuff through it. So we can handle a lot of bandwidth. We can handle a lot of signals. It's a bigger pipe to work with. But we're dealing with light waves. And what happens with light waves is as they're bouncing through that glass core, bouncing off the cladding and going the distance, as we start to get longer distances, we start to get out of phase. And that bigger pipe makes it easier for signals to get out of phase. And that's why multi-mode has a max distance of about 1,000 feet, whereas single mode is a much smaller core. That single mode core keeps those light signals grouped much more tightly. The waves are much more tightly grouped. And because of that, we can go longer distances. And when I say longer distances, I literally mean a 4K 6444 HDR signal going out 20 kilometers before we start to get out of phase. Now, as I mentioned, single mode doesn't really have a minimum distance. So we can use it in a lot of those shorter run lengths. People often ask, well, why don't I just standardize on single mode? And the reason is because there's a price conversation that we need to have, right? 90% of the applications do fall within that 1,000-foot distance, especially in the AV world that we play in. And within that 1,000-foot distances, we see that 90% of the time, people are going with multimode cable. It's the vast majority of the installations are multimode. Now, multimode cable is actually a little bit more expensive than single mode. There's more glass that goes into the manufacturing, so the cost is a little bit higher, which again raises the question, why don't I just use single mode? If it can go shorter distances, if it can go longer distances, if it's less expensive, why don't I just standardize on single mode? And the reason is because of the electronics. You got to plug this fiber into something. Single mode electronics tend to cost more. There is a higher delta on the electronics. And for that reason, most manufacturers build for around multimode is the standard. That is where you will see the most cost-effective overall installation. Rule of thumb, again, over 1,000 feet, go single mode. Under 1,000 feet, go multimode. Now, the next thing we really have to talk about here is different grading on the fiber. Okay, and this is a BIC standard chart. And what I mean by that, this is one of those data IT world charts that really speak to the global big picture. And the different grades, so fiber can be graded depending on the glass optical quality, from an OM1 when we're dealing with multimode up to an OM4. OM4, and now you're even seeing OM5s, are the higher grade fiber. It's a better optical quality, meaning we can send more bandwidth and we can send it further. In the single mode world, there's really two ratings, OS1 and OS2, okay? Real world, we see a lot of OM3, OM4, and we see OS2. Now, I mentioned that I like to throw a caveat on this chart. This is great when we're talking about networking, okay? A lot of people look at this chart and say, well, hang on, does this mean that my cables aren't really going to push 8K very far? And no, that's not the case. This chart does not just take into account cable quality, because frankly, glass cable, so that optical cable, has virtually unlimited bandwidth. And I'll show you a chart here in a minute. This chart takes into account the electronics that go with the cabling. That's what brings the bandwidths down. Simply, we haven't had the electronics get caught up to the capabilities of the glass cables yet. This is a moving chart. We are constantly doing revisions to the chart as new electronic technology comes out. The fiber optic cable itself actually handles up to 10,000 times more bandwidth than a Cat5 cable. So when we think of pulling fiber, we have more than enough bandwidth to handle just about any signal that we're going to work with in our lifetimes. The capabilities there, the electronics need to get caught up. We've been talking a lot about cable. Let's talk a little bit about connectors. There's a couple of different connectors that we will see in these different installations, these fiber optic installations. There's 5 in general: the LC, the SC, the ST, and the MTRJ and MPO. LC and ST really speak to all of the networking and the AV installations that we run into. Now, the first one that we look at is the LC. This is becoming the standard connector. This is what we see on SFP modules, which are those networking modules that are used with fiber. They are a smaller connector. It's a Lucent patent. A smaller connector means that we can fit more connections on the physical devices, and the physical devices can be of smaller size. Very handy, very nice, okay? We can compare and contrast this to an SC style connector. This is known as a subscriber connector. This is what we saw in a lot of GBIC modules, and we'll look at the difference here between an SFP and a GBIC in a minute. But the punchline is it's a bigger connector. It's what we saw in a lot of the older networking devices. More and more people are moving away from the SC to the LC. The good news is they terminate in really the same way using the same tools. And if you run into an installation that has an SC connector terminated on the cable and you don't want to actually cut that cable and re-terminate, there are adapters. There are crossover cables. The fiber itself is indistinguishable. It's the same fiber. It's just the connectors on the end of it. So it's fairly easy to adapt from one to the next. Now, electronics. We haven't spent a lot of time talking about electronics. There's a lot of moving parts here. One of the important things that I do like to hit home with, make sure people understand, is there's two ways to engineer your electronics when you're dealing with fiber optics. What's known as an external module fiber connection and an internal module fiber connection. Two different ways to make your products, very different ramifications when you build in each way. We at TechLogix, we build in both ways. So we have equipment that uses SFP modules. We have equipment that has an internal or the fiber connectors physically connected to the board. It's physically soldered onto that circuit board inside the product. Now, the nice thing about using an external module, we'll talk about the external module first, is that you have flexibility between different modules. So if I have a SFP port, I can pop my SFP module out, say it's a multi-mode module, and I can pop in a new module, say to a single mode module. So that one port allows me to adapt the product between different fiber infrastructures. Now, the downside of that is most SFP modules come in 1 gig or 10 gig formats. At least in the market today in 2018, the most cost-effective modules for the real world are 1 gig or 10 gig. Now, if we think back to that chart we looked at, we know that 4K 6444 HDR goes up to 18 gig. 8K goes up to 48 gig. Those SFP modules, if they max out at 10 gig, that means I have a potential choke point in line, meaning that these boxes need to be smart enough to compress the signals. So when we use an SFP module to transmit our HDMI signals or DVI signals or USB signals, whatever high bandwidth signal we have to be able to compress that signal to get it to go through the SFP module. Now, a internally designed product where there is no module in line doesn't have this issue. Now, we don't have the flexibility of being able to adapt from one infrastructure to the next. Usually, we are set at 1,000 feet, right? That's how most of these products are engineered. You got 1,000-foot distance, whether you use single mode or you use multi-mode, doesn't matter. You got 1,000 feet to work with. But we have no choke point in line. These are the boxes that are setting us up for 8K. These are the boxes that do fully uncompressed video transmission, fully uncompressed, networking, embedding all these signals together. This is the technology that's really taking us into the high bandwidth future. I mentioned GBICs and SFPs. There is a difference. The GBICs are what we saw in a lot of the older network devices, whereas SFPs are what we're seeing on modern electronics, network switches, access points, routers, and even some of those AV extenders. AV extenders are available in a lot of different formats. You can get HDMI only versions. These are available from a handful of manufacturers, though it's a fairly exclusive club right now. Not a lot of manufacturers are offering HDMI over fiber electronics. I expect you will see that change, especially since we are seeing the 8K displays and sources starting to hit the market. But today, not a lot of options. But you are starting to see volumes increase. Now, there are also HDMI and control versions. And this is interesting because these devices, when you look at them, anybody who's done twisted pair installations knows that these extenders look a lot like an HD-based-T extender, right? They have HDMI ports, they have control ports, depending on the model, Ethernet, ARC ports. The only difference is instead of that RJ45, you see a fiber connector. These are purposely engineered that way, so we have a familiar platform for different folks who are used to using a copper infrastructure, right? You engineer your systems in the same way. Instead of copper, you just put fiber in line. And that's how a lot of these products are being developed. There are matrices. I would be remiss to skip over the fact that there are large matrix switching products out there. They exist for fiber. But what we are seeing, instead of large matrices, more and more people are going to AV platforms. AV over IP is where we take an encoder, basically a transmitter, and a decoder, which is basically our receiver, and run those signals through a network switch. Now, a lot of people are turning to AV over IP systems. Most are copper-based. A lot of manufacturers do this very, very well. It's definitely a maturing technology. We can think of fiber optics as a way to do this better. And when I say better, we have a larger pipe. A larger pipe allows us to do more with the signals, i.e. we can send higher bandwidth signals, we can send more signals simultaneously, and we can do it with 0 frame rate latency. We could spend hours just training on AV over IP systems, especially the fiber-based system. But in a nutshell, basically, 10 gig fiber optic based switches, these are becoming readily available. They're from a lot of different manufacturers now. You take your fiber based encoders, you take your fiber based decoders, you tie them all into the network switches, which you can even get these in card based now. So you really have a lot of flexibility in the size. And that is your fully distributed audio, video with integrated networking system. Okay. Fiber allows us to do all this faster, longer, higher bandwidth. That's what fiber really brings to the party. Now, last slide that I have before I look at a couple of questions here. People always ask, what are the recommended cabling runs for different infrastructures and for different pre-wires? Here's a couple of different options that we recommend. There are some minimum strand points or strand counts, I should say, that run between your different points of demarc or different distribution points. Again, some people pull simplex. I never recommend pulling simplex. It really, from a cost difference, you really just don't see a lot of cost difference either. You always want to look at least 2 strands from a bare minimum. With that, I invite you to put any different questions that you might have into the question window in the GoToWebinar widget. I will give it a minute here for people to load any questions that they might have. I will also remind you that there is a handout in that GoToWebinar widget. We have a TechLogic's Fiber Optic Pocket Guide, which goes over a lot of the content we looked at today. And then, of course, there's a lot of information online. Feel free to reach out to any of us directly. We can help with any of the engineering that you might have. We do have a question from some folks on here about the presentation. Yes, this is a CDA deck that we teach. We are happy to send this out to folks. Simply email us. You will get an automated email after this webinar, and we can respond with the presentation deck. And then some other folks ask if it is being recorded. It is, and we will also send out the link for reviewing and forwarding this presentation on. So with that, I would like to thank everybody for joining us today. Again, fiber is becoming a very important part of our installations as AV professionals. Hopefully you got a lot out of this. We do hands-on trainings throughout the United States. We do them at CD as well. It's a great second part to this training where you actually put your hands on the fiber and terminate and see how to test the different runs and how durable this stuff is. If you'd like more information on that, feel free to reach out as well. With that, I hope everybody has a great afternoon, and thank you again for your time.